All right, so we'll look at this last exam as preparation for our final exam. Also, just as a reminder, the final exam itself is open note and open book. So, you should take advantage of that. But more importantly, you should take advantage of the fact that you have the chance to write notes, right? So I wouldn't necessarily, right? Open book can be a bit of a drawback, right? Because you can spend too much time going through your book for the correct answer. So I would recommend making a sheet of notes. I'd recommend preparing for it just the way you would for exam 1 and 2. Full sheet of paper, front and back, right? Sheet of paper, front and back. That way you can review a whole lot of stuff and try to basically condense it down to the important stuff. Then bring that as basically your first point of reference. And if it's not in there, and you would probably know it's in there because you prepared it. If it's not there, you can check your notes or the book. And if it takes too long, just move on to the next question. Don't, try to do it smartly. Okay, so let's see. This question was kind of weird, so I'm going to skip that one. I like this next one, though, because it's relevant for the series of questions you're going to get on the evening exam. Okay, so we've seen a lot of different data structures. Here's the ones that they list. They've got list, either a linked list or an array list, a 2D array, a stack, a queue, a hash table, which can be used for a set or a map, right? Hash table, set, map, you can use either terminology. Tree, binary search tree, undirected graph, directed graph, and then we finally also hit a directed acyclic graph. So for each of the following applications, indicate which data structure is the most suitable and give a brief justification of your choice. For data structures like trees and graphs, store what's in the vertices and the edges. And then if the edges happen to be weighted in graphs, tell me what the weights are, what those weights represent. Okay, so fairly straight. Once we get this, it's pretty straightforward. This is from Washington, so a lot of these are Washington references. So a map of the Puget Sound Highway system used to display traffic travel times on a web page. The map displays the principal cities, the intersections, and the major landmarks, the roads that connect them, and the travel times between them along these roads. Travel times along the same road may be different in different directions. So what data structure should we use for that application? Not a map. A graph. What kind of graph? Is it directed or undirected or directly? It'd be a directed graph, right? Because you can travel some roads are one way, right? Okay. So now, in that case, what are the nodes? What are the vertices in this graph? Easier question. What are the edges? Sorry? Well, that would be something that's what might get stored in the edges. But what are the edges? Roads are the edges, right? And your nodes are your cities, your cities, your intersections, and your major landmarks. They're the places you want to go to, right? Remember, it's just relationship. Graphs just map out relationships. Graphs just map out relationships. So nodes are, places you want to go. The edges are how you get to them. And the weights in those edges are, as you mentioned, travel time. How long it's going to take to get there. This one should be familiar. A chessboard, an 8x8 board used for a game of chess. Each square contains either empty or contains a chess piece. So that would be a 2D array. 2D array of characters, even if you want to get specific, or integers if you want to do that. That's fine. Okay. A computer model showing the dependencies between the steps that are needed to assemble a B-787 aircraft at Boeing's Everett plant. Yes. It's still a graph. What kind of graph? Undirected, directed, or directed acyclic? You're talking about directed. There's no weights, right? But that doesn't mean, but weights just means unweighted. It doesn't have anything to do with directed or undirected. So remember, the key term here is the dependencies. The dependencies, which are steps you have to take in order, right? In order to take this step, we have to do these things first. So what kind of graph describes that? A directed acyclic, right? Just like the course prerequisites, right? Just like course prerequisites, a directed acyclic graph, would be able to do dependencies. In fact, that's what they're used for primarily in computer science, for figuring out, okay, if I'm going to, like, so let's go ahead and let me boot up my bash shell on Windows, which is kind of weird to even just mention. And say I want to like sudo apt install let's say open SSH an open SSH server, right, so that people can log into my system. Right, let me type in my password. So now, it says it's already in there. It says that the following package is automatically installed and no longer required. Libra free types. In fact, let me do a different one. Let me install TextLive on this. I know it's not going to come to that because it's a huge amount of files. It says in order to install TextLive, I need all these packages to install, which is a lot of programs to install TextLive, right? Because they're all dependencies. I need all of these things for TextLive to be installed, and TextLive needs all these things to build stuff in LaTeX, and it needs a lot of stuff to build that. So it's basic. So it uses directed with graph to know, okay, so TextLive needs these things, and these things need these things, and these things need these things. So we're going to install the things at the bottom first that don't have any dependencies, and then we're going to install the next things and the next things. So that's how it's used. 900 megabytes of disk space will be used. So, I'm sure if I did full, tell me 4 gigabytes of space would need to be used. So okay, so directed acyclic graphs are great for dependencies. All right, a list of legal words in a Scrabble trademark TM game. Okay, we want to be able to quickly check whether words are used by players, in fact, do exist in the list. Right, so we've got our dictionary file like from the assignment. We want to store that in a data structure so we can check it quickly. So what data structure can we use to confirm that it just exists? Don't care where it is, we just want to know it exists. ArrayList, not really. Okay. A set is the choice that we need. Or a hash table. We want that because sets, they are good at checking. They're good for checklists. Like if you can check if something is in a set in constant time, right? With ArrayList, if it's in order, you'd still be doing log n time. You'd be doing log n time, but we could do faster. If we want to check it as quick as possible, we could do it in constant time with a set. That's why we also say to justify your answer, because then you can get partial credit for making an argument. A description of the inheritance relationships between classes and interfaces in a Java program. Right? Now remember, a class can extend another class, right? And if that was just the case, that would be a tree, right? But you can also implement multiple interfaces, right? We can implement multiple interfaces. So that generalizes that relationship from a tree to a graph, right? Just to prove it to you, I'll just show you from all the way back in chapter 2, right, where it talks about the lists, right? ArrayList implements the random access interface, and it's also an abstract list, right? So you have multiple. So it's got 2 parents in this case. So this is a graph of some kind. It's a directed graph because, I inherit you and you inherit that guy. It's not, So this just means something. So is it directed or directed acyclic? It's a directed acyclic because because again, you're talking about dependencies here. What you're inheriting from one specific person or another, or one specific class or another. Okay, so another one. The history list recording sites visited by the user of a web browser. As new sites are visited, they are added to the list. The list also supports the operation of going back to the previous web page or forward to the next page. So, tree? We don't really have to make any branching connections, so not a tree. Sorry? The linked list? Yeah, linked list works for this one. The instinctual reaction I got from a lot of students in the afternoon class was a stack, but a stack you can only backtrack. You can't go forward. With a linked list, you could go forward and go back, right? And you're just going to be adding stuff to the, to the essentially either the front or the end, depending on your point of view. All right. So nodes in the binary tree are represented by the following data structure: a BT node, because they need to distinguish, because they feel like they need to distinguish that from the node class. It has an int item, it has a left node and a right node. Right. Complete the definition of the method BFS below to perform a breadth-first traversal of a binary tree and print out the node data's values in the order they are reached during the search. So we're going to print out stuff. In your solution, you can create and use instances of whatever other data structures you would like: lists, queues, stacks, trees, hash tables, graphs, or whatever. And their operations, if they are useful, without giving details to implement. In other words, you can assume you can use any other data structure right here. So breadth-first search, right? We have 3 traversals in order, or we learned about 3 traversals before the final, before we started reviewing. We learned about in order, post order, and pre-order. Breadth-first search does not fit either of those patterns, right? It's the root, then the level below the root, and the next level after that. We remember from one of the examples we did last week, that's level order traversal, right? So this is one of those 10% of the tree problems that can't be solved, that we don't want to try solve using either the search algorithm or the other traversal algorithms. In fact, we don't even want to use recursion to solve this one because it's breadth first search, right? Just because it's a tree, don't let it fake you out. This is just, a tree is a graph, remember? So you just do breadth first search on the tree, right? So let's see how that works in practice, right? It's just breadth first search on a tree, which means the only thing we need for this is a queue. We don't even have to keep track of the nodes in the set because this is essentially a directed graph. We're only ever going to our children. We're never going to risk, hitting the same node twice. Okay, let's do this. So Q is equal to, technically I have to put a new linked list here because Q's are interfaces, right? If I remember correctly. And then Q dot, I think the term is offer, but if you use add or in Q, whatever. Q dot offer, the exact terminology for Q in Java I don't really care about. But it's offer. And I think it was R. So offer the root there. So now while there's still stuff in the queue so while the queue is not empty, I think it's actually is empty, but I think there's also an empty method. Is empty. So while the queue is empty, so it is not empty, do the following. Get something out of the queue, so q.poll, E-O-L-L, node current, I think technically it's a BT node, but whatever. Node current is equal to q.poll poll to get the front thing in the queue. System dot out dot println current. Okay, and now what do we need to do? We need to add our, since we're doing breadth first search, we look at our left child and our right child and we add them to the queue if they exist, because there's possibility they're nulls, right? So and I can either add the nulls and have an if statement over here to handle them, or I'll just do it over here. If root sorry, if not moved up to the left, but if current dot left is not equal to null, q dot offer sorry, current dot left. Then I'll add the curly brace there, and then I'm just going to be lazy and say do same for right child, right? And that's essentially the entire algorithm. So while it's not empty, get the current node, print it out, and then if you have a left child, add it to the queue. If you have a right child, add it to the queue. Keep doing this until the queue is not empty. And then we're done. And always remember to print out the node you just dequeued. Here's another useful question. So here's an adjacency list representation of a directed graph. There's no weights in the edges, right? And adjacency lists, right? They're representing it as a linked list. So A is connected to B, C, and D, right? That's what this says. B is connected to A, C is connected to B, D, and D is connected to has edges to nobody. So it's saying draw the picture of the directed graph above. So we'll draw this graph, which is actually fairly straightforward, right? So we've got 4 nodes, A, B, C, and D. So A is connected, this is a directed graph, so A is connected to B, C, and D. B to A, C to, and let's see, and C to B, and C to D. As I told the afternoon class, on their exam, but not on your exam, they're going to be expected to be given an adjacency matrix and draw a graph that results in this. Okay. Although we'll go ahead, we'll put the nodes in the right order so that the connections are less loopy. Yes.
And you get the opposite.
I think in my final exam, I just simply skip straight to what I consider important, which is doing Dijkstra's algorithm. So I don't have time to waste with this stuff, but I consider it more important. Like, given this graph, please figure out do the traversal algorithms on it. They have to do that too, but they have to draw it first. And I don't see a reason why to change that for the common final because it's a common final. So now another way to represent this is an adjacency matrix. So draw the adjacency matrix for this graph. So to draw the adjacency matrix for this graph, right, we have A, B, C, and D. A, B, C, and D. Source, destination. 1 if there's an edge. 0 if there's not. So zeros all the way down the diagonal because nothing was connected to itself. A is connected to, has edges to B, C, and D. So 1's over here. B goes to A. See, was there anything else that B was connected to and I just happened to miss it? Nope, B just goes to A. Okay. And doesn't go to anywhere else, so 0's there. C goes to B and D. And D doesn't connect to anybody, doesn't have edges to anybody else. All right. Another Dijkstra's algorithm problem, if we want to go through that. but we already did one, so I'm gonna jump back to it at the end if we need to. But I've already covered it in the other lecture if we don't get the chance to go back to it. Okay. Let's see. So two of the most common divide and conquer sorting algorithms are quicksort and merge sort. In practice, quicksort is often used for sorting data in main storage rather than merge sort. Give a reason why quicksort is likely the preferred sorting algorithm. Basically, so quicksort, are they talking about main storage in the, let's see, do they have a solution? Nope, because I'm just trying to figure out what they mean by that. Oh, they do. Right. Okay, so there really wasn't. Okay, so main storage, so assume RAM, rather than merge sort. In practice, quicksort is often preferred. But I think by main storage, that's I'm just like, do they mean RAM or do they mean disk? Right, and I think they mean disk. So give a reason why quicksort is likely the preferred sorting algorithm for sorting on a disk rather than your RAM. So let's think about merge sort versus quicksort. Performance-wise, on average, how did they perform? Right? If we were concerned about if for some reason the worst case was the determining factor, then we'd use merge sort all the time because its worst case is n log n, and quicksort's worst case is O of n squared. But obviously that's not a factor because if that was, we'd use insertion sort and be done with it. If we didn't care about if the worst case scenario was what we were judging this on, and for some reason we couldn't use merge sort. So we're obviously looking at the average case where they're equal. They're both n log n. So why would you use why is quicksort preferred then? Why bother with quicksort? What's the disadvantage of merge sort? Now, and I think we went over this earlier. What's the disadvantage of merge sort? It uses memory. You have to basically split it in half, right? You have to have an extra space to do that, to copy all the stuff over and then so you can merge it, right? If you're trying to sort O of n items, you have to have O of n storage. N items, you need O of n storage, which is a pain. Quicksort can be done in place, which is why if you're doing on disk, you might want to do it that way. Now, in practice these days, I think timsort is pretty much used for everything, but I'm not sure about that. So, all right. So the second question, which is more straightforward, I think. Quicksort's worst case runtime is O of n squared, but it has an expected runtime of n log n if the partition function works well, right? Meaning we split it in half. What needs to be true about this to well, I just answered that. What needs to be true for the partition function in order for running time to be n log n? And the answer is it has to be able to ensure that we can split the array into rough halves, right? In practice, how do we ensure this happens? Bad news, we really can't. Now we can't really ensure it that it happens, but we can modify the partition function, right, a bit. Right, rather than just selecting the first item as the pivot, we can kind of grab a random sampling of the other items, right, and basically choose the median of those items as our pivot, right? We can that way that we aren't just going to be sorting only to one side. Okay. So let's see what else. There's not too much else in there that we've got. So, let's see. So that was the Harvard one. So we've gone over this. So I feel pretty comfortable with what we've gone over. So let's go ahead and talk about how would you find some more stuff if you need practice on your own. So data structures, right? Look for data structures, final exam. Specify Java if you need to, but if it's done in C++, you can pretty much figure it out. If you need to be specific about it because you're ending up with like flashcards on websites or something, use file :PDF to look for just PDF files. Now, typically you get something like this, and typically you'll find that basically they follow pattern. Like here's data structures 89-120, right? And this is the answer one, right? So, and generally if you can, generally you can find stuff without the answers. You just got to figure out what it is. Or if somebody has it, you can figure out what their answers are. Right here is another class which has the solution for this one, but the thing you have to remember is that not every exam will basically cover all the things that we will have. Sometimes stuff that are like here's a 2-4 tree that we didn't study, that we haven't studied, right? And that's something they do in that class, like Kruskal's algorithm. So this seems to be much more of a data structures with a bit of more algorithm stuff in it, right? Rather than us where we focused on making sure we knew a lot of Java in it. So don't be afraid if you find stuff and you don't know and you don't know the all the answers in it, because it's likely the case where basically we didn't cover it in class. If it looks familiar, then maybe you might want to double check that it was in our textbook, because remember, we went over pretty much everything in the textbook except for chapter 9. All right. So honestly, I think that's it. So I think we're done here if you want to end early. Do you want to end early? Yeah. All right. So we are done. Good luck on your final exam. I'll stay behind to grade stuff and whatnot.